I often say that at some point in my career, I became more of a XGBoost modeler than a machine learning modeler. That's because if you were working on large tabular datasets, there was no real point to try another algorithm. It would provide close to optimal result without much effort. Yeah, okay, LightGBM and Catboost are obviously as good and sometimes better, but I will always keep a special place in my heart for XGBoost. So let me show you how this algorithm was put together. In a previous video, we looked at how the gradient boosted trees algorithm works. Now, I'm going to show you how XGBoost improved on it. Doesn't that feel like some fresh air in this Gen AI madness? Let's get into it. So what does that mean to train a tree? Well, we have an initial dataset, so it has some features and it has a target. Each column represents a variable and each row represents a sample in the training data. And training a tree means that we're going to split the training data recursively by looking at the different values in the different columns. For example, we could imagine that the first node of a tree could look at column A and decide that we need to split based on the value lowercase a. So each of the samples where the column A have the values lower than lowercase a goes left. Each of the samples where the column A have the values higher than the lowercase a, they go right. We recursively iterate this process, so we look at this new subset of the training data, and again, we look at the different columns to find the right split. So here we could imagine that the split would be happening on the column B, and that every sample where the column B has a lower value, that lowercase b, they go left, and each of the samples where the column B has a higher value than the lowercase b, they go right. And we recursively iterate this process until we reach the leaves of our model. Reaching the leaves of our models means that we stop the splitting process. We stop the splitting process because we met the conditions like there's too few samples in one of the nodes, or we met a condition on the depth of the tree, and we stop the splitting process because of it. So there are many ways we could stop the splitting process. So now when we arrive at a node, what column should we choose and what value we should choose to split the remaining data? So the problem we want to solve is this. We have a set of trained trees already. So now we want to add a new correcting tree. How do we build the next tree? So knowing how we build the trees will help us understand how we should split the data at each node. To understand how to build a tree, we need to understand the concept of loss function. A loss function is this optimization function that we want to minimize such that we optimally build the tree. So how do we build a loss function? Well, you could imagine that the loss function is related to the error that we are making every time we are predicting, and we want to minimize the error every time we are building a new tree. The concept of error is related to the concept of loss function. We want to minimize the errors and we want to minimize the loss function. So let's dig deeper into this concept. In XGBoost, we have the loss functions that is split into two terms. We have the loss functions where we sum over the different samples in the training data, and we have the piece where we sum over the different trees that we have already built. So we have the piece of the loss functions that is meant to minimize the bias, and they introduce a new piece in the loss function that is meant to control the variance. So we saw that we want an algorithm that has a low bias and a low variance, and there's always a trade-off between the two. So instead of trying to minimize one or the other, we are building a loss function where we can try to minimize both at the same time. And we're going to have some hyperparameters that will help us put more or less weights in the different terms in this loss function. So the first term here is meant to minimize the errors that we are making between the predictions, y hat, and the target, y. So y hat is the predictions, and y is the actual target in the training data. So omega here is meant to represent the complexity of the different trees, and we sum the complexity over the different trees. When we want to minimize the bias, we have a loss functions that we would like to minimize between the predictions and the target. So you can see that we have a loss function that we can measure at the sample level between the target and the predictions. Here we sum over the trees, so it's a complexity that we measure when we build the trees. So this omega function is also decomposed into two other terms. We have here the first term that is equal to gamma t. So capital T is a number of leaves. This means that if we minimize this loss function, we would like to minimize the number of leaves in each tree. So this will minimize the complexity of a tree. If we have less leaves in a tree, we're going to have less complexity in that tree. We also have another regularization term where we want the prediction in each of the leaves to be a bit smaller. So this term omega is going to push the number of leaves to be lower and is going to push the predictions to be smaller. We don't want the prediction of each of the tree to be too big because we don't want to induce too much impact each time we are correcting with a new tree. This will help us minimize the overfitting. So the first term is meant to make sure that we are not underfitting, and the second term is meant to make sure that we are not overfitting. So let's look at the sample level loss function. This is a function that is going to compare the predictions to the target. For example, we could use the mean square error loss function. We could use the cross entropy function. So there are many different loss functions that we could use depending on the specific learning task. So for example, if we are trying to solve a classification problem, most likely the loss function would be the cross entropy function. So what is this equal to? So here we have the sample level loss function, and this is the target. So when we look at the predictions, we have the predictions of the previous trees, and we have the prediction of the new tree. This is the set of predictions to predict the target of all the previous trees, and here is the new contribution of the new tree. So this is a way to decompose the predictions. Now we are focusing on building a new tree. And what we want to do right now is to learn the f function such that we are minimizing the error that we make when we are predicting the target. X here are the features. So this is a set of features that we are putting into the new tree, and this is going to provide us with a set of predictions. So here is this sample level loss function. Again, we decompose the prediction into the prediction of the previous trees plus the prediction of the new tree. But this is hard to use as such because depending on the analytical form of the loss function, we may not be able to find a way to learn the new f function. The typical strategy to learn the new f function is to decompose this sample level loss function into a sum of terms. And to do so, we're going to use the Taylor approximation. Here, what we are doing is a second order Taylor expansion. We are approximating this function by expanding the original function into a sum of terms. So you can see that we have the first term here that is a loss function that is related to the previous trees. So this is the error that we were making with the previous trees. And here we have the gradient times the new tree. The gradient is a derivative of this function here with respect to the previous predictions. The gradient represents the slope of this loss function here. The second term is introducing the second derivative of the loss function. The second derivative of the loss function is called the Hessian, and the Hessian is multiplied to the square of the new tree. This approximation is exact when the prediction of the new trees are very small, when they are going towards zero. So far, what we did was just some math. We just expanded the original loss function into an easier loss function to use. That is an approximation, but that provides an easier analytical form for us to manipulate. So now we have this new loss function. So here, this first sum is meant to minimize the bias. And when we add this new tree here, we want to make sure that we minimize its complexity as well. We don't need to take into account the complexity of the previous trees because they are just a constant that we already learned in the previous iterations. So when we are minimizing a function, if we add a constant to it, it does not change anything, so we don't need to add it here. The only terms that depend on the new tree are those three here. So here, this is a loss function that we were measuring when we looked at the previous trees. In the context of learning a new tree, this term here is a constant. These are terms that we can change depending on how we build the new tree. So this one does not depend on the new tree. So we don't care about constant. The optimal solution to minimize a function will not change if we add a constant to it. So we don't need to look at this full loss function. We can discard this term here because it does not involve the new tree, and we can focus only on the terms that involve the new tree. So minimizing this function here, this new loss function, is equivalent to minimizing the original function here. So let's make a trick. So let's look again at this loss function. Here we are summing on the samples, and here we are summing on the different leaves in the new tree. So let's do a trick to change how this formula looks like. So when we look at this sum over the samples, we can decompose the different samples in the way they sit in the different leaves. If we look at all the different leaves, we're going to find all the different samples in the training data. So summing over the samples is equivalent to look at all the different leaves and then to look at all the different instances in each of the leaves. So we can decompose the sum over all the samples into a sum over all the leaves and a sum over all the instances in each of the leaves. This is good because here we had a sum over all the different leaves in the tree, and here we had a sum over all the samples. So it was hard to mix the different terms between the different sums. But now that we have a sum over all the different leaves in the tree, we can now mix the different terms in the sum. You can see that this weight here can go here and can be summed with the Asian. So F here is a tree. But if we look at the different predictions of the tree, they're going to be equal to the sum of the different instance weights at each of the leaves. So here we are decomposing the predictions of the tree F here into this W weight here. So now the game is how do we find the different weights for the different leaves? These are going to be the predictions in each of the leaves. How do we find them? How do we compute them? Well, what we can do is to use a concept of optimization, where to find the minimum of a function, we take the derivative of it and we equal it to 0. When the derivative of a function is equal to 0, we reach the minimum of that function. And the solution of this equation here is given by this formula. So here are the optimal weights that allow us to minimize the loss function. So let's try to think about this. We had a loss function. This is a function that we wanted to minimize. To find the weights that minimize this loss function, we took the derivative of it and we solved the equation by equaling it to 0. And the solution of this equation is a set of weights that depend on the gradient, the Asian, and this lambda function that captures the concept of complexity. And we can take those weights and we can inject them back into the loss function. When we inject them back into the loss function, we obtain this new optimal loss function that takes into account the optimal value for the different weights. So we've seen a lot of math so far. But when it comes to finding the right loss function, we followed a very straightforward path. We engineered originally a loss function that will help us minimize the variance and the bias. And by following optimization principles, we obtain an optimal loss function. And it happens that the analytical form of the optimal loss function is this one. This is something that we can easily compute in code. We need to make sure that the analytical form of the sample level loss function that we choose can have a gradient and can have a Asian. As soon as we know what are the gradient and Hessian, we can just compute them, and this is very easy to compute in code. But how do we use that to find the right split in a tree? In a tree, we have the parent node, the left child node, and the right child node. We go left to go to the left child, and we go right to go to the right child. So what is the right split? Well, we're going to use this loss function to find this right split. What we want is to understand what are the different instances that we want in the different leaves. So we want to make sure that the different instances are going to minimize the loss function that we can measure at the leaves. And to find the right loss function, what we do is we look at the loss function that we measure in the parent node. We look at the loss function that we can measure in the left child node, and we look at the loss function that we can measure in the right child node. We want to make sure that when we move instances from the parent to the left and right child, we want to make sure that we decrease the loss function. So we want to find the split that will minimize the sum of the loss function in the left node and the sum of the loss function in the right node. So in a sense, what we want to do is we want to find the split that will give us the biggest decrease in loss function between the parent and the children. So this is the way we're going to use this loss function to find the right split. Let's try to understand a bit more this loss function. This is an interesting form of the loss function. What we have here at the top is the sum over the instance gradients squared. And at the bottom, we have the sum over the instance Hessians plus this hyperparameter here that controls the complexity. So what we have here is at the top, we have the gradient for the leaves, and at the bottom, we have the Hessian plus this lambda factor. The Hessian, the second derivative of a function, is also called the curvature of the function. So when we want to minimize the loss function, what we want to do, we want to find the gradient that are maximal, because the highest gradient with the minus will minimize the most the loss function, but we also want to have the curvature that is minimized as well. If we have a low curvature, this whole function here will be maximized and we will minimize the whole loss function faster. So we want to maximize the gradient and minimize the curvature. So what does that mean? So here we look at two different functions. We have a function that has a low curvature. We don't have a lot of wiggles in that function. And here we have a function with a lot of curvature. XGBoost is going to try to weigh the decrease of the gradient and the decrease of the curvature. If we were to look at a normal gradient boosted tree algorithm, the gradient boosted tree algorithm would take the split that would maximize the decrease in the gradient, but would not take care about the curvature. XGBoost would tend to take a split that is more conservative, where the decrease in gradient is not as much, but to make sure that the curvature is not as much as well. So now that we have this loss function, what is the algorithm to find the right split? So let's imagine that we look at this specific node here, and we are trying to find what is the right column and what is the right value on that column to split. So how do we proceed? So in principle, we need to iterate over all the different columns, but let's imagine that at this point of the process, we are assessing the column C here. And we have different values in that column, and it is related to different values of the target. The first step is to sort the whole dataset by the values of that column C. If we sort the values of that column C, we can see how the different split in that column C can separate the different values in the target. So for example, if you look at this specific split, where we split in between 3 and 2 here, you would see that the target will be exactly separated. So splitting in between 3 and 2 here is separating the different classes in the target, and it allows to perfectly classify the different instances of the training data. So the way we proceed is that we need to look at the different splits, and we need to compute the different values of the different loss functions. So we need to compute the values of the loss function of the left child if we were to split here, and we need to compute the value of the loss function of the right child if we were to split here. You will notice that the loss function of the parent is actually a constant. It's not changing if we are changing the value of the split. So this does not really matter in finding the split. So we iterate through each of the possible splits that we have in that data. So we look at each of the splits that would split the column, and we find that the split number 2 here is the optimal split. It is a split that is maximizing the difference between the loss function of the children and the parents. So if we want to find the optimal split when we are looking at a specific node, what we need to do is to iterate through each of the different columns and iterate through each of the possible split in each of the different columns. And we choose a split that maximizes the difference between the loss function measured on the parent and the loss function measured on the children nodes. So when we look at gradient boosted trees, because it is an iterative process, we need to build each tree one after the other. So if we want to parallelize the algorithm, what we need to do is to parallelize the search of the split itself. So what we could do is to assess the different columns in parallel. We could try to find the split for each of the different columns in parallel. We don't need to iterate to do that. And we can take the best split on each of the related columns and find the overall best split over all the columns. So each of the threads is going to provide the best split on column A, the best split on column B, the best split on column C, the best split on column D. And in the main thread, we're going to sort out and find the split that is maximizing the difference between the loss functions of the parent and the children. And we could imagine that the resulting split is done on the column C with the value lowercase c. So when we find the splits, how do we deal with missing values? So let's assume that in the training data, we have some missing values here, some values that are meaningless. So how do we handle missing values with XGBoost? The way it is done is actually very simple. We proceed with the same process than before. We sort the whole dataset by using the specific column we are looking at, and we are putting the different missing values on the side. Let's imagine that we are looking at this specific split. First, what we do is we assume that the missing values, they go left. So that means that we're looking at the target of the instances that relate to the missing value, and we are putting them in the left node. And we can compute the difference between the loss function of the parents and the children by doing this. Now we can do the opposite. We can take those instances and we can put them into the right node. And again, we're going to compute a difference between the parent node and the children nodes. By assessing putting the missing values left or putting them in the right node, we're going to see what is the difference in loss function that is going to maximize the difference between the parent loss function and the children loss function. And we could assume that in this case, the difference is maximized when we put the missing values left. At each node, we're going to assess the missing values differently, and the missing values will be assigned a default direction, left or right, at each of the nodes. So we saw two of the main features of what introduced XGBoost at the time. We saw a way to mathematically formalize the concept of complexity in a tree to make sure that when we build trees, we build more optimal trees. So this way we can try to minimize the bias as well as trying to minimize the variance in the same time. And we have this parallelization of the split search that allows to have very fast training times considering the type of iterative algorithm. But there are additional features that we are not going to cover. Let me give you a rundown of the different features that we are ignoring here. But first, all the columns are pre-sorted, while keeping a pointer to the original index of the entry. This removes the need to sort the features at every search. When I show you how we do the split search, we need to sort all the features every time. Instead of doing that at every node, we can pre-sort the columns such that the search is faster. Sorting has a time complexity of n log n, so it is good to not have to redo this step over and over. They use the compressed column format for a more efficient distribution of the data. When we parallelize the model, we need to send the data on different threads of the CPU, so it is interesting to have a specific format that allows to do that efficiently. They use a cache-aware prefetching algorithm to minimize the non-contiguous memory access that results from the pre-sorting step. When we pre-sort the data, we change the order of the data, and the way the data is localized physically in the memory is changed. So the access of the data would be slower if we were not doing this step. A big piece that we ignored is that they also provided an approximated split search algorithm. Instead of considering each of the split in the data, so at each of the instance on the data, we can build histograms of the different columns, meaning that we can group instances together. This means that when we search for the different splits, we don't need to assess as many candidates. We can just look at the splits that relates to the histograms.